Hey everyone, my name is Frank Bodin and I'm going to present you today CPU Affinity with and without workload partitioning on Red Hat OpenShift. First, a disclaimer. You can pause the video and take the time to read the whole disclaimer, but the key takeaway are that this material do not represent any official statement of position of Red Hat. It's provided for educational purpose and should not be used in any production or mission critical environment, and there is no SLA attached to it. Okay, let's have a look at a typical server that is part of our data center on which we run Red Hat OpenShift. Those servers are usually dual sockets, and each socket has a memory and devices attached. So that's what we call NUMA node 0 and NUMA node 1. And now if we look at the CPU socket 0, so it's this chip embed a lot of what we call core, physical core 0, physical core 1, and those core are composed of two hyperthreads. Hyperthread 0, hyperthread 1 of the physical core 0 belonging to CPU socket 0. And those hyperthreads are the Linux CPU, which are also the Kubernetes CPU, because Kubernetes reuse Linux CPU concept. There is no Kubernetes CPU concept, it's just Linux CPU. So those CPU, those Linux CPU, are numbers going from 0 to max CPU minus 1, and do not give you the information about their physical layout. If they have the hyperthread of the second core on the first or second NUMA socket. So it's not something that is visible. So in order to manage this kind of locality, you need to use CPU manager, topology manager, NUMAware scheduler features, which are orthogonal to this presentation. And here we're going to focus on Linux CPU. So first, let's have a look at what is running on an OpenShift node. And for every component which is running on an OpenShift node, on which CPU it's allowed to run. And we are going to do that for a node without any tuning. So out of the box, we install Red Hat OpenShift node, and this is what you're going to get. Meaning, so there is no performance profile created. So here we have our 12 CPU, as before as an example. So IRQs can run on any CPU. IRQs are hardware processing events triggering work in the kernel. So this is kernel work triggered by interrupt. Can be packets arriving on a NIC, can be NVMe IO operation, etc. We have systemd units. Systemd units are basically all of the user land on an OpenShift node which are not pods. So typically kubelet, SSHD, IRQ balance, etc. And then you have the Red Hat OpenShift pods, which can be best effort or burstable QoS class. So for both of these classes, there is no limit on CPU usage, but it's optional for burstable. And you have guaranteed QoS class pods where request equal limit. And then you have the user pods with the same class of pod QoS. So let's simplify the view because pods are all equal without workload partitioning. So everything can run on any CPU. And the question is, who's deciding what's running where? So IRQs can run anywhere, but a given IRQ is going to be pinned on a CPU by IRQ balance systemd unit based on the activity of that interrupt. Let's say the interrupt from my NIC is very busy, and I've got a second NIC which is also busy. IRQ balance will make sure that these two IRQ do not hit CPU 0, but is going to put one busy interrupt on CPU 0, for instance, and another busy interrupt on CPU 2. It has its own spreading algorithm, but the key takeaway is IRQs are tried to be spread as equally as possible on all CPU. And then you have systemd units and all of the pods. They are all Linux userland processes. And where they run is decided solely by Linux scheduler. And by default, there is no restriction. Everything can run on any CPU. So how to partition CPU on Red Hat OpenShift? So in order to do that, you need to use an object called a performance profile. So a performance profile permits to create two partitions, the reserved partition and the isolated partition. And the key element of this configuration is that reserved partition plus isolated partition should be all CPU. You should leave no CPU behind. You should not forget any CPU, because if you do so, you're going to have a system that will behave unpredictably. And so the key takeaway is no, you don't forget any CPU there. And if you have doubts, you can always use the performance profile creator tool with the link here in order to help you to create those masks for you. Because here it's very simple on the screen because we have only 12 CPU, but reality is more complex when you have dual socket system with 512 CPU, for instance. So, okay, I've got two partitions. I've got a reserved partition, I've got an isolated partition. So, but reserved for what? Isolated from what? Good questions. And it depends if workload partitioning is used or not. And it depends if guaranteed QoS pods with integer limits are running and are properly annotated. So, what is allowed to run on which CPU without workload partitioning? So we have our reserved CPU partition, we have our isolated CPU. So, IAQs can run on any CPU. Systemd units are confined to reserved CPU. Best effort and burstable QoS class pod can run on any CPU. Guaranteed QoS class pod with non-integer limits can run anywhere. And guaranteed QoS class pod with integer limits can run only on isolated. So basically, guaranteed QoS class pod with integer limits are limited to isolated CPU. Systemd units are limited to reserved CPU, and the rest, IAQs and other pods, can run anywhere. One thing to notice is that the overall CPU consumption of all of the pods cannot exceed the isolated CPU count, because from a Kubernetes scheduler perspective, the available CPU to schedule pod on a given node equal the number of isolated CPU. So this is how Red Hat OpenShift works. And of course, this is equal of the overall amount of CPU minus the reserved CPU number. Okay, so this is why you should not leave any CPU behind. And this is true on this picture about this very nice separation until a guaranteed QoS pod start with integer limit and properly annotations. So with proper annotation. So let's start a pod with proper annotation, but without workload partitioning. So what's happening is that pod is pushing away all of the other pods from its CPU, but IAQs can still run on the CPU. So again, this is without workload partitioning. And if you add the proper annotation on that pod, still without workload partitioning, you can exclude also the interrupt from that CPU. So the pod P has a full and dedicated access to CPU 10 and 11 in that example. Okay. So now let's add workload partitioning in the mix. So what is allowed to run on which CPU with workload partitioning and with a performance profile? Because workload partitioning only works if you have a performance profile created, because workload partitioning is going to use reserved and isolated partition. So as without workload partitioning, IAQs can fire anywhere and systemd units are confined to reserved CPU as any node with a performance profile configured. Then Red Hat OpenShift pods now are restricted to the reserved CPU. So with workload partitioning, the Red Hat OpenShift pods are confined to the reserved CPU, so we can isolate the user pods from everything but the IAQs. And the other way to think about it is systemd units are going to be collocated with Red Hat OpenShift pods. So all of the infrastructure of Red Hat OpenShift plus IAQs are going to run on the reserved CPU. So this is true as before until a guaranteed QoS pod with integer limits and properly annotated starts. Okay. And by the way, Red Hat OpenShift pods do not require to have these limits and this annotation. They don't need dedicated CPU like a CNF does. Okay, so what's happening when you start with workload partitioning the same kind of pod as before with the proper annotation? Well, the user pods will have these two CPU dedicated, not available to them, and they will run on any isolated CPU not running this kind of pod. So if you start a lot of these pods, you want to make sure that you have enough isolated CPU in order to run your other pods if they need to be collocated with that pod. But you can just let the Kubernetes scheduler place the pod for you. To summarize, Kubernetes uses Linux CPU concept and do not reinvent its own CPU concept. So a Linux CPU equal a Kubernetes CPU. The performance profile object define two sets of CPU, the reserved CPU, the isolated CPU. On those CPU, you run pods. And there are two kinds of pods. The pods pinned on a list of dedicated CPU, and those pods can only run on isolated CPU. Those pods have request equal limit, and request and limits are integers. All other pods, the pods which are not pinned on a list of dedicated CPU, they will be running on any online CPU not dedicated to a pod of type 1. And they will also respect workload partitioning constraints, meaning that the OpenShift pods will run on the reserved partition, while the user pod, the CNF pod, are going to run on the isolated partition. Finally, only a pod with pinned CPU can be excluded from IRQ processing as long as it has the proper annotations. Thank you for your attention. Have a great end of day.